Be giving a perspective on chemical and process engineering, and really from the viewpoint of global warming. But I'm going to start. I'm going to start by tackling the technology. Just a little bit of chemical engineering, so you can see where that fits into issues of global warming. We're interested in chemical engineering, and we always say transforming bulk raw materials into some useful product. And I'll give you some examples in a moment. Scientists, we say, work out the chemistry, they work out what reactions are going to happen, what we need to do at a molecular level, and it's the engineers and the chemical and process engineers who scale it up so that we can get products at a large enough quantity that are going to be useful for you. We're not chemists, we're definitely engineers. We want to do that safely with economics and with environment in mind, and now with global warming in mind. So some examples. Chemical engineering started really with oil processing, when people got oil out of the ground and they wanted to make petrol and diesel from that. And that's absolute core traditional chemical engineering. And then we take the oil and we can react that, and we can make plastics and other chemicals that you use daily without a thought. Or there's mining. We don't get involved in mining too much, but we'll get involved in refining ores and in making metals like aluminium or steel, things like that. But it's not just those standard chemicals. Within New Zealand, we do a lot on wood processing, so this might be making MDF, medium density fibre board, making laminated lumber, paper, pulp, all sorts of things like that is big industry in New Zealand. Food processing, is a big industry in New Zealand, and that is a highly complex sort of process industry, and we've got a bunch of our graduates work in that, in trying to optimise and design those processes. Beer and wine is another one. Our graduates sometimes go and work in that. And we could say that one of the successes of the New Zealand wine industry is they've taken the stainless steel technology from the dairy industry and the expertise we have in dairy and applied it in a way that perhaps some of our competitors overseas haven't, and hence we've got an advantage because of that. Applying good engineering, but not forgetting that the grapes are special. But today I want to talk quite a lot about energy, and so I thought I'd put in some slides about our current thinking on some of the energy and some images here. People have talked about biofuels, and we're getting concerned that these might not be as wonderful. The image on the top left is a bioalgae system, and it looks really pretty because you get this lovely green algae. But the problem is producing enough diesel to keep the trucks of New Zealand or the world going, and it just doesn't seem to stack up particularly well. Others I've got there in the text that have been tried, biodiesel from corn. It works in the States, but it's pretty marginal from the point of view of how much energy you have to put into it and how much energy you get out of it. Sugarcane, it works really well in Brazil, and there's some parts, Brazil's the main country, perhaps in Queensland and Australia might work, but nowhere else really is going to be worthwhile. Biodiesel from vegetable oil, biodiesel from tallow and things, pretty marginal for making our trucks go. There's so much energy has to go into those, and carbon dioxide is released that it's just not necessarily a good return. Algae, I've mentioned, I don't think that's going to really fly except in some really special cases. And palm oil is one of the ones that's of interest at the moment. People are worried about palm oil in their chocolate or palm oil kernel that Fonterra is importing for food. The biggest problem with palm oil is the CO2 that's emitted by chopping down trees and not having trees soak up CO2. So the total emissions are significant from that. So I want to talk a little bit about that, because from an engineering point of view, we're interested in the case of oil, extraction or refining, or in the case of a biofuel, where chemical engineers are interested in the refining business on this. And it's easy for us to come up with some really good processes that are fuel efficient. But the real issue with a lot of these new energy sources is what they call this indirect land use change, and you sometimes see it as ILUC and sometimes with capital, indirect land use change. And that's the bit. So it's saying you chop down some trees, no longer have you got the trees absorbing carbon dioxide to grow, and so your net emissions actually grow. And that's shown a little bit on the right in the graph. Here we've got CO2, grams of CO2 per megajoule related to the different fuels. We want to get a certain number of joules out, but we don't want to emit CO2. And so there's petrol and diesel are sitting there. But if we look at some of those others, soy biodiesel, we've got all this here, and palm oil is even worse, which is related to changing our use of the land and trees being chopped down and grass being displaced with other things. And so we become almost even with petrol in terms of emissions of carbon dioxide. So the thing about this, and I don't want to go into the calculations, but we call it a life cycle analysis, LCA, and that's what engineers and some agricultural people will get in there as well, and some scientists there as well. And what we're trying to do is look at all parts of our possible renewable energy and look at the entire life cycle, right from where we're clearing land or mining or whatever it might be, to see what the net impact is going to be. Some other sources, people are saying, well, corn's not so good. What about wood? Yeah, wood is looking promising because wood, as you know, the trees grow nice and tall. There's a huge amount of biomass in trees, so it's a really dense source. And people are looking at gasifiers and other things where we can take wood and we can produce liquid fuels like petrol and in fact other chemicals there as well. And it's looking as if these are going to be more energy efficient and more carbon dioxide efficient, but will they be good enough? Who knows yet? We're working on it. Then the other big thing in terms of energy is materials, and the chemical engineers get involved in this, other scientists get involved, physicists, and the materials, the obvious ones there, silicon cells. Some of us, I think, really believe that that is going to be the future in the world, harnessing the energy of the sun directly. And so issues of making appropriate materials, and it doesn't need to be silicon, but it could be silicon-based, could be impure silicon, that's going to be really important. And along with that, car batteries. And you're probably too young to realise how batteries have just changed enormously with the lithium batteries that you have in your cell phones. They are just so much better than ever before, and we're really hoping that that advancement, scientific advancement and materials advancement will continue, so we get some really good batteries that we can use to store electricity, to put electricity into our cars. I want to look at some issues, and I want to bring it a little bit closer to home, but we talk about peak oil first. Is there enough oil in the ground? And when I was at university a number of years ago, people said there's only 10 years or 20 years of oil left, and there still is 30 or 40 years of oil left, plus. We now know that peak oil is not an issue, and I say here there is enough oil, gas and coal to fry the earth. Right? The issue no longer, and things have changed there, the issue used to be, will we have enough oil? And the answer now is yes, we know we've got enough oil, and if we burn it, we can fry ourselves very successfully. Right, so the issue becomes one of greenhouse gas production and reducing our CO2 emissions. So it's not fuel supply, it's CO2 emissions. And so what we can have here, we can either use renewable fuels or reduce our energy consumption. And what I want to do is concentrate on that second one, because I think this is where you and your families and your parents and anyone else you know can make the greatest contribution, because you're not going to be going out there and developing renewable fuels. If you become a chemical and process engineer, yes, perhaps. But I think you can reduce your energy consumption. And I'm going to look at a number of examples where you probably can, as individuals, make a contribution. So let's look at our energy. Global energy consumption, 560 EJs. Anyone know what one of those is? I always figured that I could start with joules. Kilojoules are okay, I can manage that. Megajoules. Oh, very good, very good. Do you know what comes after mega? Giga? Yeah, oh, you're good, you're good. Just losing my microphone. Peta. Oh, and then we get exa. 10 to the 18. I can't count with a number that big. It's too big. 10 to the 18, 10 to the power of 18 joules. I don't get it. It's just. So let's just look at New Zealand, and I can manage that. I might be able to have some influence in New Zealand, but even then, 550 petajoules, 550. What's that by 10 to the power of 15 joules per year? That's too big for me. I can't imagine all those. So I'm going to see if I can individualise that a little bit. I'm going to look at our population, about 4.5 million, and I'm down to 120 by whatever that is, gigajoules per year. Still a lot. I'm going to go down to days. I'm going to go down to a day. 330 megajoules per day, and I'm going to see what I can do about that in some way. I can just about manage that. It's about 100 kilowatt hours if you think in terms of electricity. Kilowatt hours. That's total. That's not just electricity. You're using that for petrol and transport and all sorts of other things and flying around. I really want to concentrate on what you are doing and what you can change there. And one way of doing that is to look at how we use energy in New Zealand and to get the big numbers. And we just total it up. So there's our total, 540. And the big number, and we concentrate on the big number here, is the 202. And of that, we'll see in a moment, petrol is 104. And that's the bit that you and I and your parents and whatever are responsible for. It's a huge lump in terms of emissions. We'll concentrate on the big numbers. So some of those other ones, industrial's big, but it's made up of some smaller bits. We're also going to have a look at residential because that's you at home and what you can do there. So the petrol for your cars, just say a bunch of you came by car today, either to university or perhaps to school or whatever. We use 104, whatever, gigajoules per year. 23,000 megajoules per year per person. Is that going to be any use to us? I'm not sure, but that's roughly what it is. I want to look at the emissions you get from that. And I can Google this. I just Google what's the CO2 emissions from petrol, and I get this number. It's all on the web these days. What's that? 75 grams of CO2 per megajoule, and you're using, and this is for each of you. This is not just per car. This is the entire population. You're using 23,000, so we can work that out. 1.7 tonnes, 1,700 kilograms of CO2 that each of you are responsible for, even when you're a baby and being carried around in the back of the car in the car seat. Right, so you've got some there. And that's out of the total, and I haven't given you this figure, but the total for New Zealand is 7,700 per person. And that ratio is actually really important. So the biggest lump of your CO2 emissions is coming from the car that you're driving or being driven in. That's the biggest single proportion. So what can we do there? And your choice, and it's interesting because when people make the choice about the car, the global warming is left at home somewhere, or that's something for the States to work out. When someone goes and buys a new car, the last thing in your mind is, how is this going to contribute to global warming? And I think it should be the first thing in your mind. Or in your dad's mind, if he's the one who's making the decision. Or have a go at your grandparents as well, if they're making that decision. Now they've got a bit of money and can think. So what? Your choice. What are you going to do? Are you going to get one of those nice big cars that you can take up skiing once every 2 years that does 10 litres per 100 kilometres, or you're going to get a nice economical 6, which is about the good standard these days. And we can work out, and we'll do the same sort of calculations, and we can Google this and see how much carbon dioxide is emitted for every litre of petrol. And that's carbon dioxide that's coming from the carbon in petrol. It's also carbon dioxide that's been used to transport it, to process it. It's all sorts of carbon dioxide that's been produced through the life cycle of petrol. And if we can do it, let's say we do 14,000 kilometres per year, 10 litres per 100 kilometres, 2.4 kilograms of CO2 per litre. And I've intentionally written it this way. We do this a lot in engineering so that we can make sure that our units are just cancelling out really nicely. We've got litres there, and we should be left with kilograms that's of CO2 per year. If you buy one of the gas guzzlers, or your dad buys one of the gas guzzlers, what do we got? 3,400 kilograms of CO2 per year will effectively be emitted from that. What was the total? 7,700 is the average for New Zealand. You're almost half of that if you buy a gas guzzler, I call it that. Whereas if you buy an economical car, you're making much less contribution. And this is the first one where this is a choice that we do the calculations, and I dare say this is the engineering. We do the calculations on this to see what the impact will be, but the choice comes down to you. You can't leave global warming for someone else to sort out when you're buying your new car, or your dad's company or your mum's company is buying a new car. So you try and have some influence, will you? The shower. Now, here's getting close to home. Okay, so you don't buy a new car, but you do have the shower, don't you? And we can look here at electricity use, because the shower is pretty well run by electricity, at least in the South Island. Some of you might have gas. What have we got? 44 gigajoules per year. So we've got 10,000, I've worked this out, 10,000 megajoules per year per person is how much you're using for electricity at home. Let's see if we can work out how much your shower is doing and how much CO2 has been emitted because you're having a lovely shower. I don't know whether you've come across this at school anywhere, perhaps not. Energy is mass times what we call specific heat content times a change in temperature. So we can work out easily from the mass of water that comes out of your shower and how long you take. That's just flow rate times time. You can do that. You can get a bucket. You can get one of those laundry buckets and see how fast it fills up. And if you try some showers, you go from about 6 litres per minute up to 20 litres per minute. That's a really strong shower, isn't it? And it feels really good, and the 6 feels just marginal. Or if you're my mother, she can have a shower in 2 minutes. I manage about 3, but some of these teenagers, I understand from one of my own, it takes about 10 minutes. Is that right? Time yourself sometime, will you? So the shower, the amount of water you can use in the shower goes from 12, the nice frugal person, perhaps to 200. That's all right, I'm not paying the electricity bill, but what happens, right? So let's work it out. Energy, MCP, T hot minus T cold, work it out. And so we're going from 1.5 megajoules up to 25 megajoules for the shower. Huge range. Now, you think in the South Island that your electricity is coming from the dams. Well, it kind of is, but we don't have enough dams in New Zealand. So when you spend a minute longer in the shower, they're turning Huntly up. And Huntly Power Station is a coal-fired power station. So when you're in the shower for just a little bit longer, for a minute longer, we burn more coal in New Zealand to provide that electricity because we don't have enough water in the dams. So we have to be thinking about how much CO2 is going to be emitted from Huntly by burning coal to provide the electricity for you to have another minute in the shower. And we can work this out, and if you have a nice short shower, this is the very efficient shower, you can be, this is CO2 again, you could be emitting over a year 150 kilograms of CO2. But if you're one of those people that like the long shower and you've got one of these really wonderful volumetric showers, you can be up to 2,400, 2,500. That was up there with the car, right? And compared with our average 7700, right? So you think that your shower doesn't affect global warming, and I'm telling you it does. And I want you to have short showers, and I want you to go home and measure how much water comes out of your showers, and if it's not less than about 8 litres per minute, you tell your parents it'll be worthwhile money for them, and it'll be worthwhile for carbon dioxide emissions for you to get a low flow shower head. And it'll be worthwhile to put a timer on it as well. All right, how are we going? Oh yeah, a few minutes. So, do you see what I'm getting at? Your choices are the ones that actually matter. It's not Obama's choices or the President of China's choices. You are having a significant impact. Now, a problem I deal with on a daily basis is, should I put my sandwiches in cling film or Glad wrap? Should I put it in a snap-lock bag? Or should I get one of these renewable containers that I can wash again? And I've got the data up there. I've measured this when I got this and had 120 metres, and I measured it and it said it was about 460 grams full. That's what engineers do, they measure the mass of these things. And then when I make my sandwiches, I've rolled it out and I've got the tape measure and I use 1/2 metre, almost exactly. So I can work out exactly how much mass of plastic I use if I'm wrapping my sandwiches in that. Mass of plastic if I'm using a bag, or mass of plastic if I'm using one of those. There's the numbers. 2 grams, 4.2 grams, or 76 grams. It's all polythene, believe it or not. As a chemical engineer, I can look at the process and say, how much energy have we got going in through the oil that comes, how much are we losing, how much process energy are we having to put in to heat it, and we come up with this concept of embodied energy. How much energy has gone into the production of this? And we get a number, and I'm going to use 80 kilojoules per gram, that's the lower end of the estimate from that. And I want to apply that to see which one comes out best. All right, so for this, for my lunch, 160 kilojoules, 340, 6,100. Yes, but I reuse this, don't I? I reuse this, I'm going to wash it. But there I have to apply that other equation like the shower, and I have to work out, there we go, how much I'm washing. Cling film, no washing. Bags, possibly none, but you might rinse them out and use them again. And this one. Now I had a go to wash it, and I measured how much water it took me to wash this with some other stuff. And I figured 500 grams is the least I could do with my sink and the hot water. And in fact, I worked it out for the dishwasher as well. And I said, how many of these can I fit in the dishwasher? And I figured it comes out about the same sort of energy requirement. It's an odd household, ours, that we just measure things all the time. Right? So then we add on that, and the numbers come out here. So this is 160. If I use these ones 3 times and I use 300 grams of water, I can get 180, but I've got to use this 3 times. And in our household, they don't get used 3 times, I'm honest. If I use this and I manage to keep it for 100 uses, then I'm into the same sort of number. And I manage to change those so they're all the same number. Right? I don't know what you're like, but in our household, these do not last 100 uses. They disappear. The kids take them to school and they're gone in a few weeks. Or they go in the dishwasher and these break off. They don't last 100 uses. My lunch, Glad wrap, cling film, right? So that's looking like the best energy option. And I can do the same. I can work out how much carbon dioxide is emitted to make that, and that. How much carbon dioxide is emitted when I wash them. And there's the numbers for my carbon dioxide emissions from my choice of making sandwiches. Right? Glad wrap wins. Only 5 grams of CO2, even if I reuse those, 21 grams, and this one here, 31, because of the plastic in it and because of the reuse. So that's just an example there of the sort of analysis that we can do and you can do, but we apply this on a much larger scale to work out what impacts we might have from different processes. So your choices are important, and whether it be the choice of vehicle or the shower you have or lunch wrap, or, ones we haven't talked about, air travel, whether you've got LED lights. If you don't have LED lights, or if you've got some of those old light bulbs at home, just replace them, you'll save your parents money. your home heating decisions, all those are decisions that you are making that will impact global warming. Now, as a chemical engineer, if you choose chemical engineering, then you can have decisions on terms of the sorts of processes we use to make plastics or fuels or something like that, and you can make another sort of contribution to reducing global warming. Okay, and that concludes what I've got to say today.